Started. It's go time. Take that down. We're already live. It's over there. Oh, it's actually taping. Wow. I was actually having them write this down, but you could hear how loud they are and how some aren't actually doing. Okay, here we go. Maybe they've calmed down. And then actually started taking us down. Okay. So, who uses every edge once? It's Euler, path or circuit. I lost my pen too, so I get to do that, and then come back to this. There we go. So that is what Euler path and circuits do. So I just wanted to make a point that this is different and just play along with it. Hamiltonian path uses each vertex exactly once. May or may not use every edge. Probably won't use every edge. And then there's a contradiction. See if you can pick it out. A Hamiltonian circuit is a path that uses every vertex once. Is that possible? Because what has to happen with a circuit? Yeah, it has to come back from where you started. So, of course, you have to use the vertex you started with twice, right? Do you get it? You understand? Little contradiction. So everything in the middle, use every vertex once, and then you end where you started, so yes. The one you started with, you have to end at, so blah, 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 blah. So just in demonstrating the paths, and by the way, answers what? Answers what? Vary. Okay, if I start from A to G, yay! And then G to F, then F to E. So far, have I only used a vertex once, right? No double use. E, where'd I go? E to D, D to B, and then B to C. That's a path. That is Hamiltonian because each vertex is only used once. Back, 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 back. For this one, that's A to G. How exciting. G to F. F to E. E to D. D to C. C to B. How many times has each vertex been used? Once. And I started at A. So when I end at A, that is now called a what? That is called a Hamiltonian circuit. Every vertex was used once before that. A couple edges are not used. But every vertex is used, and you end where you start. Ain't no thing. The next concept of the day is what's a complete graph. All right. So, complete graph. It's a graph which every pair of vertices is connected by exactly one edge to each other. So every vertex is connected to another one with one edge, not two. Remember we learned that B could get to C two different ways. That's like having two different bridges to connect this island to land. That does happen in some scenarios. Not in a complete graph. One edge to every vertex, but every vertex is connected to each other. It's a complete graph. Couple formulas. Everything else up to this point, I think, has just been knowing the terms and knowing how to do it kind of stuff. Knowing what an Euler path, Euler circuit, following along, blah, 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 blah. All those things are just, then the simple math is just adding, subtracting, mostly adding. Find, smallest numbers. And we're going to do that again with Hamiltonian. But here's some numbers to play along with. Here's some formulas. Number one. Darn tootin' might have to be memorized. It's responsibility, I guess. Put it on a note card. Whatever. Synthesize the chapter by writing all the important components. This is one of them. So specifically for a complete graph, the number of vertices is n. So in this case, it's 5. We have 5 vertices in this little example. The number of edges is 5 times what? What's 5 minus 1, everybody? 4. 5 times 4 is 20. 20 divided by 2, 10 edges. There are 10 edges in this drawing right here. So that's what this formula means. If you have a complete graph where every vertex is connected once and only once to every other vertex. So if there were 7 vertices, which I might or might not go through that example tomorrow in the book, 7 times 6, 42 divided by 2, 21 edges. What I'd have to do is draw, what's a 7-sided figure, by the way? Ooh, that's interesting. I thought sept was 100, though. I've heard of sept, but it's actually heptagon, right, is what I've remembered. I think sept is something different. All right. And then, hey, here's this math again. And then I'll actually pull out the calculator. What is this called when you have n exclamation point or 5 exclamation point, which means 5 times 4 times 3 times 2 all the way down to 1? No, what's it called? You just said it. Factorial. So we do have a factorial. Again, this is how many Hamiltonian paths that are unique exist in this. So again, answers may vary. Hey, give me a Hamiltonian path. Okay, well, I could start with B, or I could start with C, I could start with D, I could start with E, and I could start with A. That's 5 different ones already. But then, if there's 5 factorial possible paths, I threw this little nugget of information out. How many different paths are there starting from A? Well, the simple math would be, how many vertices are there? 5. If there's 120 total different paths in all of this, how many just starting with A? 120 divided by 5, which we found out in first hour was 24. So there's 24 different Hamiltonian paths just from A alone. Blah, 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 blah. So they have silly little questions about that, just dealing with this math, which really I think it can only be guess and check. They say there's 1 billion something or other different edges. How many, different edges. How many vertices are there? They might ask that. I don't know about 1 billion. So really what you do is guess and check. Here's your 84 calculator. This one's a little weird where it's at. And then anyone that has a scientific will have to, go by and figure out where it's at. 84s, pay attention right now. I'm not doing this for you anymore. Okay, because I'm mean. So if I want to do 5 factorial, 5, I got to type 5 first. Then you actually go to math. Math is the third button down from the left. Math. And then, see, this is not very easy. And then you go over to PRB, probability. Then lo and behold, it's number 4. Not easy at all. Press enter. I'll do it one more time. 5, math, probability, 4. And then we did do 5 times 4 times 3 times 2 times 1 to get 120. For an Inspire, love the Inspire. Actually, Inspire, I don't know if it's easier or not. It actually is just one button click, though. But you got to find a button. So waiting for it to open. Waiting. Boom. Okay, very small written calculator. No, I don't. Okay, where was it? It's the pi button. Where's the pi button? I lost it. Oh, it's right here. You can barely see it, but I hit it in red. So now you can see it in red right here. All right, and then it's this exclamation right there. So you'd have to hit 5 first, hit that red button, and then exclamation. You play along with yourself. Now, every scientific calculator is different. If you have a scientific, I'll have to hit you with what to do after I'm done with this, which won't take long. Well, then you're on your own. Okay, so Hamilton Path, we have 120 different possibilities. Just to exercise it, here's E to A. Okay, and I have a whole bunch of different ways I can go after this. A to C, C to D, then D to B. It's a Hamilton Path where an edge is not used twice. Every vertex has been connected. Okay, so that's what's going on with that. And then if I go back to E, then I have created a circuit out of it. And that's the only point of that being written. So Hamilton Path, if I ask you to find one, there's 120 different possibilities. Ugh. All right? And then for the circuits, you just go back to where you started. So you can just finish it off by going back to where you started and make it a circuit. And then very similar to what we did last week before a quiz, finding at least cost, in this case, a Hamiltonian circuit. Now, this is how I want you to do number 25. Ignore the directions. 25 is the last number you have to do. 25 is not as large as this example. So you have to do less. Okay, I'll give you a hint. This example has how many vertices? Don't count the crosses in the middle, like when they cross. There's 5. Number 25 has 4 vertices. So at the end of this, we'll find out how many different things do you have to write for 25 if you do what I'm asking you to do here. So move in. What we're putting on this completed graph, let's be aware of what we're putting on this, is similar to what we put last week on our other stuff. A weighted graph. Put numbers on it which mean, let's use money because we all relate to money. We want to spend less. So this weighted graph, it cost me like $6 to go from E to D, $7 to go from D to C, $12 to go from C to A. It's really hard to kind of write these and keep track of where they're at. So make sure you don't get lost in what number is going with what edge, I should say. And this be $10 amounts, which they don't really have to be. They could be, how long it takes to get somewhere, or the distance. And of course, the distance we translate into maybe money. What we want to do is find a Hamiltonian, very easy for me to say, circuit that costs the least. Okay, very similar to what we did last week with different concept. Game there. Change the game. Okay, tell you what I was thinking at first what would work, but watch what happens. You would think you'd start at, just looking how it starts, do you think what might be best? Who do you think you might start at? What vertex? I'd pick one of two would be your most probably obvious. What do you think? E or D? Why? What's the number on E and D? What would you really start at, E or D, though, if you really were thinking? E, because if I started at E, okay, and this, I'll tell you how I was thinking when I first read this, and I thought there's one answer, but there isn't. So if I start at E and go to D, that's what I would think to do first. So this is what you want to do. You want to write the path, and then write the number that you get when you go from that to that, which is 6. So it costs us $6 to go from E to D. Let's pretend $10. I would go that way because then from D to C is the next smallest number, right? So that's plus $7 more. Now I'm stuck because it has to be a Hamiltonian circuit. So now from C, I only have 2 choices. It's to A or to B. Which one's better? A. Okay, that's not so bad. And you want to write that, A. This is what you have to write for your work to be shown. It's not a big deal. Well, last hour I was having conniption fits over, this is hard. Okay, I only have one choice. What's my only choice for a Hamiltonian circuit? I can't go to D or E because those vertices are already used. I must go to B, which is the biggest number out there. So this may very well not be the best, cheapest Hamiltonian circuits. Okay, now what do I have to do to make it a circuit? What do I have to do? End at what? E, which is what number? 14. Uh-oh, we're missing something here. Hold on. What? Somebody actually picked up their finger and typed buttons. It's amazing. Did anyone verify that number? Y'all should be trying to help me out, but Okay, now, so where do we start at? E. So starting at E, that is the best path starting and ending at E. There is no better one. But is there a better overall starting somewhere else, like D? Well, if I start at D, where do I have to go? D to E. Okay. And then what's after that? Okay, so E to 16, 14, 12. 12 is better. So E to A. So E to A, Oh, I didn't write my first one. 6 plus 12. Because if I don't, in last hour I tried to do all the path and then write the numbers, and I got confused. Okay. Now what? Now what do I do? Can I do 11? Nah. No. So what do I have to do? 12 or 19? Which one's better? 12. So A to C. So I have to explain it, so that makes it take longer. You will not take that long, and plus you only have 4 vertices, not 5. So stop whining. Wow. Where do I go next? C to what? C to B, right? Now are all the vertices used? But what do I have to do? End where I started, which puts a what in it? 8, but it puts an 18, right? Okay, and then we can add those. We'll do that offline. It'll take us like 5 minutes to get there. Too cool for school, 61. All right, I think I got 2 people verified. Are you okay back there?
61, my brain verified it.
Oh, gosh. All right, let's move on. So it's taking long because we're explaining it all. So now where do we start? Start at who? I don't know. A. I didn't get my pen. Okay, so A to who? We start at A. A goes where? D. The smallest one's 11. Let's try to do this and keep track of it. Now that I'm here, where do I go? 6 or 7? 6. So 11, 6. Now where do I go? It has to be, B or C. It can't be back to A. So it's B, which is 14. So 6, 14, 11. Then what? Not 19, not 18. It has to be this one. And I started at A, so may I go back to A? Yes. So starting at A, I went A, D, E, B, C, back to A, and it was 11 plus 6. Oh boy, 11 plus 6 plus 14, right? Plus 13 plus 12. And I think I heard it. It was what? 56. Okay, and then just for purposes of getting the notes complete, I will finish the last 2 on the video. The only one I did not check is starting from B and starting from C. So I'll start at B. Where do I go for B? 19, 14, 18, or 13? Which one? 13. 7, 16, or 12? 7, 7, 6, or 11? Come on. 6. 6. Can't go back to B. Now I'm stuck. 12. Hey, that's the whole pentagon, right? So that one's easy to denote. So I started at E once, then D, then A. Now I started at B to check what that one would end up being. And I went B, C, D, E, A, and then back to B, and it's these numbers in order. 13 plus 7 plus 6 plus 12 plus 19, right? I think from last hour we got 57 for this. I won't even bother you. Then I'll zoom in for the last one and show you how this one is actually no different than the previous one, which can happen. Okay, and I'll just go in yellow just to make it look different. Okay, now the last one is, the only one I did not start at is A, D, E, E, C, right? So starting at C, where do I have to go? I do have to go to D. After D, where do I have to go? E. And then what do I have to do? It's either 14. See, it's the same. And then what do I have to do? I can't go there, so what? And then what do I have to do? So this one is the exact same as the other one. You end up walking around C, D, E, A, B, and then end at C, and it ends up being the same number. So which one's the best one? Which one's the cost less one? 3, starting at A and ending at A. That is the least cost Hamiltonian circuit. Done.